Hi folks. Today we're going to look at solving exponential equations, which are equations where the x, or the variable, is up in the exponent. And there's a technique that we're going to use that will require us to rewrite numbers in sort of convenient forms for us. So just as a warm-up exercise, we're going to take a look at converting these numbers that are over here into a form where they have a prime base. And a prime is a number that's only divisible by 1 in itself. So let's take a second here and think about how could we rewrite the number 9. We could call it 3 times 3. That would make sense. We could call it 4 plus 5. But it's asking us here to write it in exponential form, so as an exponent. So what I'm hoping you're going to think about is I could write 9 as 3 to the power of something, 3 to the power of 2. And so we have a bunch of other numbers over here. And I'm going to get you to take maybe, I don't know, a minute or so and see if you can rewrite them in a helpful form. We can just pause the video and then we'll go through them. You don't need to copy this down as, say, your notes. This could just be scrap work. But yeah, take a few seconds here and see if you can put these in exponential form. Okay, and we're back. So when it comes to 16, my guess is that there were two different approaches here. Probably some people wrote this as 4 to the power of 2. And some people wrote it as 2 to the power of 4. Both of those are correct. Okay, and that's not a property that holds for every number, but 16 is special in this way. Now, if we're looking for a prime number base, then it would be this one. That's the sort of required one, or the one that's being asked for. But they're both correct versions of a new way of rewriting the number 16. Thinking about 125, it's pretty fishy that it ends in a 5. So we could think, okay, 5 squared is 25. 5 cubed is 5 times 25, which is 125. So this is 5 cubed. All right, the next couple are fractions. So 1 over 25 is the same as 1 over 5 squared. I mean, that would be okay, but it would be nice to see it written just as a base to a certain exponent rather than having a fraction involved. And remembering what we know about exponents, we know that negative exponents flip stuff. They flip the result. So 5 to the negative 2 is 1 over 25. You could try it in your calculator. Depending on your calculator, it'll either say 1/25 or 0.04. They're the same thing. So looking at this next one, well, we know that 16 is 2 to the 4. 1 over 16 is going to be 2 to the negative 4. So these are all ones that we can do in 1 or 2 steps. The last one's a little trickier, so it may take a couple of steps for us to figure this out. So we've got the square root of 8. 8 seems fishy. I know that 8 could be written as 2 to the power of 3. Okay, so we have square root of 2 to the power of 3. And we also know that a square root is just a power of a half. Fractional powers are roots. When we have powers raised to powers, we multiply those powers. So I've got 2 to the 3 all to the half, so that's 3 over 1, really. Multiply these powers. This would give us 2 to the 3 over 2. And I don't know if I can get my nice purple color back. Let's see. We're close. 2 to the 3 over 2. You can check that in your calculator. It's going to give you the same decimal approximation as root 8. None of these things that we've done over here have been actually solving equations, but they're kind of prerequisite skills. So let's take a look at solving an exponential equation. And this is where our notes start, so if you want to take a second and copy this down, that would be great. You can pause if you need a little time. And thinking about this equation, I mean, we could just try some things. We could just say, I wonder if x equals 1 is a solution. Let me throw that in there. I'd have 2 to the 3 times 1 minus 1 equals 8, which would be 2 to the 3 minus 1 equals 8. Oh my gosh, is 2 squared equal to 8? No. Boo. Okay, well, that didn't work. Okay, x equals 1 didn't work. We could just try x equals 2. Okay, let's try that. I'm going to put in 2 for x. This is maybe not a great way to solve this equation. You don't need to copy these steps down. I'm just showing us a way that we could try and hunt down answers. So then you get 2 to the 5. Is that equal to 8? No, 32 is not equal to 8. This is really annoying. Just hunting for answers is not going to work out well for us. So we need an alternate approach. And the thing that you might have noticed between the two numbers that are involved here, the 2 and the 8, is that they can share a common base. I could just write the number 2 as 2, so I have 2 to the 3x minus 1, and the number 8 as 2 to the power of 3. I haven't changed any of the values here. All I have done is rewritten the number 8 in a different form, so it's still completely equivalent, the equations. Now here comes the neat part. The bases are the same. 2 equals 2. The whole result is the same. That must mean that the exponents are equal to. So we can kind of drop the bases. It's not that we're dividing by 2. We're just going to say, therefore, 3x minus 1, the exponent on the left, is equal to the exponent on the right. We only get this property because we made the same base on both sides. And then, sorry about this, and then we can solve that equation. So we have 3x equals 4, or x equals 4/3. Okay. That apparently is the answer. Do you believe it? Maybe, maybe not. I'm going to circle it or put it in a box. But I am going to check it because I think that'll be fun. And also, it asked me to check it. So if I were to put 4/3 in, I'd just put 4/3 in for that x. So I'd have 2 to the power of 3 times 4/3 minus 1. And I'd be wondering, does that equal 8? Let's see what happens. That would be 2 to the... Okay, 3 times 4/3 would be 12 over 3, or just 4. Oh my gosh, we'd get 2 to the 3, and that is indeed equal to 8. So in any equation, you can check your answer by subbing back in. But we had a set of steps here that worked, that got us a technique rather than just guessing and testing. So let's look at what that technique is. The steps for solving exponential equations. We should convert to a common base. Often that's a prime. It doesn't have to be. Once we do that, and we clean up, so I'll write that here, and clean up, we'll equate the exponents. And what that looks like is just dropping the bases. The bases disappear. And lastly, I mean, this is kind of a cheeky suggestion for step 3 on solving an equation you solve. But the resulting equation should be not too bad. It should be a linear or maybe a quadratic if we're feeling like torturing you a special way. So take a second and copy this if you haven't already. And then we'll move on to a few examples. Okay, moving on. I've put my steps over there to the right. You don't necessarily need to copy those, but you do want this question. When I look at this question, I look at the bases and go, okay, there's a base of 2 and there's a base of 4. What base could they share? How could we get a common base? Well, the common base, the easiest one, would be 2. Like, we can rewrite the number 2 as 2. That's no big deal. We can also write the number 4 using a base of 2. 4 is just 2 squared. Now, everything else in the equation stays the same. Maybe I should color code this a little better. So you can see exactly what's changing. So nothing is changing on the left. I'm just replacing the number 4 with 2 squared. And we still have all to the x plus 3. Okay, there's our first step. Convert to a common base. We also need to clean up a little bit. So On the left side, we'd have 2 to the 4x. On the right side, you have powers to powers, so those powers get multiplied. So that's 2 to the 2x plus 6. And now we're at this lovely step where one side says 2 to the something, the other side says 2 to the something. We can equate our exponents at this point, or drop the bases. Drop bases. Okay. So if we do that, we'll just get 4x, the exponent on one side, is equal to the exponent on the other side, 2x plus 6. And we can move this around, so I can subtract 2x from each side. And that gives me 2x equals 6, or x equals 3. There's our answer. Okay, and there are all those 3 steps shown. Do you believe that it's the answer? Well, we could check. If I check x equals 3, I'd have on one side 2 to the 4 times 3, and I'd be wondering if that is equal to 4 to the 3 plus 3. Is 2 to the 12 equal to 4 to the 6? You could check it out with your calculator, or maybe you have a neat analytic technique. But yes, indeed, 4096 is equal to 4096. This check is optional, but it might give you some peace of mind. We're going to do 3 more of these. And so the same idea here. We have 9 to the 4x, we have 27 to the x minus 1. I want you to take a second and think about what base might both of these sides share. One side is 9 to the power of something, the other is 27 to the power of something. What I hope you're thinking here is that the common base, or the easiest common base, is 3. Okay? Because if I think of all this, the number 9, that could be written as 3 squared. Okay? It's still the number 9, just written differently. 27, that could be written as 3 cubed. Again, it's still the number 27, but just written differently. So nothing has changed with the values here. We're just trying to put it in a more convenient form. Next, we're going to clean it up a bit. So powers to powers means we multiply the powers. On the left side, we get 3 to the 8x. On the right side, we get 3 to the 3x, and be careful here. Make sure you distribute this 3 all the way over to the x and the minus 1. So we have 3x minus 3. At this point, we can drop the bases. So we can say, therefore, 8x, you don't have to say the therefore, but it's kind of nice, is 3x minus 3. We could move the 3x over, so we get 5x equals negative 3. Or x equals negative 3 over 5. And again, we could go and check this. It's going to be a little trickier to check. Maybe you'll need some decimal approximations or some sort of fancy method, but it will indeed balance the equation. So that's a case where we had to change the exponent or the form on both sides. Let's check out another one. Here we've got 1/3 on one side and 9 on the other. Let's think about a possible common base for 1/3 and 9. Now, you could do a common base of 1/3. I think it's kind of painful, though. My suggestion is that you do a common base of 3. You don't have to. But I typically see, it get a little bit messed up when people try and choose fractional bases. Again, if you're feeling comfortable with it, go for it. You're going to get the same answer either way. But I would be thinking, okay, this side is something to the x minus 2. It's 1/3 to the x minus 2. Let me just write that as 3 to the negative 1. That's what 1/3 is. And the other side is 9 to the 3x. Well, let me just rewrite 9 as 3 squared. And again, we're just going to clean up a little bit. So if I multiply this negative 1 through, I'll get 3 to the negative x plus 2 on this side. And on the other side, I'm going to get 3 to the 2 times 3x, so that's 6x. Okay. Now it says 3 to the something equals 3 to the something else. We can drop our bases here. Okay, so we can just say, therefore, the exponents are equal. Negative x plus 2 equals 6x. And I could add x to both sides so that I'd get 7x equals 2. And we can finish it off with x equals 2/7. Again, we can check this. If you'd used a base of 1/3, that would be fine. You just have to call 9 1/3 to the negative 2, which is a little bit weird, but same result. Okay, one last one that we'll do together. We've got this one. We've got a 2 times 5 to the 3x minus 2 equals 250. What could the common base be? Well, you might want to say that it's 5. So that would be fine. On the left-hand side, we got a 5. On the right side, let me think about 5. I know that 5 squared is 25. And 5 cubed is 125. And 5 to the 4th is 625. Oh, no. 250 doesn't seem to really work to rewrite it as 5 to the power of something. Now, the other thing to notice here is that there's a 2 times up front. Okay? And as we've kind of seen over the whole course, one of the fundamental gags of algebra is that we want to isolate the weirdest thing first. So in this case, that 5 to the 3x minus 2 is the weirdest thing. What can we do to get it on its own? Well, we could divide both sides by 2. That might help. So that's kind of a 0th step, is isolate exponential term if possible. If I divide both sides of this by 2, I'm going to end up with 5 to the 3x minus 2 equals 125. And then this looks doable. So we can have a common base at this point of 5. 5 to the 3x minus 2. 125 can just be written as 5 to the 3. Great, we've converted to a common base now. Everything's all cleaned up. All we have to do is drop the bases. So we get 3x minus 2 equals 3. Or 3x equals 5. Or x equals 5/3. And there we go. We're done. Okay. So if we've got a situation where there's a coefficient out front, maybe you want to divide that out and try and isolate that exponential term. Just for fun, we could check here. Does this work out? If I have 2 times 5 to the 3 times 5/3 minus 2, I'm just subbing in for x. Will that really give me 250? Let's check it out. That would give me 5 to the 5 minus 2. Is that 250? Let's see. Or 2 to the 5 times 5 to the 3. That's 2 times 120. Oh my gosh! It really does give us 250. Yay! Okay. So we can check. It's not required. We've got our basic technique here. Hopefully you have that copied down, the 1, 2, 3, and maybe step 0 as well. We're going to do a bit of practice. So here is our practice. There are 5 questions up top. Those, I think, are fairly straightforward. Maybe number 5 is getting a little challenging. After you do those 5, I'd like you to head to page 364 and do number 4, 5, and 7D. And then if you get all that done, you can either finish up with any graphs that you didn't get done on Monday, or do the following challenge questions. So the number 6, 7, 8 below. The alleged solutions are down below. Hopefully they're correct. And I will see you folks tomorrow. So we can just leave this slide up on pause so that it's up here, and you can just copy the questions as you're doing them. Good luck with the material, folks, and I'll see you soon.